Hello and welcome to The Explainer. Okay, so we're all in on electrifying our world, right? But there's a problem, a huge bottleneck really. We're struggling to test the super complex electronics needed for our future grids and transport. We've kind of hit a wall. But what if I told you a simple, elegant shift in thinking is completely changing the game? Let's dive in.
Think about it for a second. It's a massive puzzle. Before you spend billions building a new high-speed train or a next-generation power grid, you have to be sure its electronic brain, the controller, is going to work perfectly. But how do you test a controller for something that isn't even built? Well, the answer is simulation. But, as you'll see, the way we've been doing it is starting to break down under pressure.
So here's the deal. Our whole net zero future really depends on these incredibly powerful electronics that manage huge flows of energy. But designing and, more importantly, testing the megawatt-scale systems for the grids and electric transport of tomorrow, well, that has become a major roadblock.
And the scale we're talking about here is just immense. I mean, look at this. A single 2-megawatt power electronic transformer can have almost 600 power switches inside. And they're not just sitting there. They're all firing thousands of times every single second. It's like a high-speed, high-power orchestra. So the goal, the dream really, is to test the controller for this whole system virtually, long before a single piece of hardware is ever built.
Now, engineers test these controllers using a really clever technique called hardware-in-the-loop simulation. It's a brilliant idea in theory, but the traditional approach is completely handcuffed by one single thing: the tyranny of the clock.
Let's break that down. Controller Hardware-in-the-Loop, or CHIL, is basically a flight simulator but for electronics. You take the real physical controller, the actual brain of the system, and you plug it into a completely virtual power system running on a computer. The controller thinks it's running the real deal, which lets engineers see exactly how it'll behave under any condition you can imagine, all from the safety of the lab.
Okay, so the old way of doing this is time synchronized. This means the simulation has to keep up with a real-time clock, perfectly, step for step. For every tiny slice of time, we're talking like 100 nanoseconds. It must finish its calculation. If it's late, even by a little, the whole thing fails. The analogy here is perfect. It's like trying to draw a hyper-detailed blueprint on a conveyor belt that is just flying by and never ever stops. Sounds impossible, right?
Well, it kinda is. This rigid time limit causes huge problems. To stay on schedule, the simulation has to cut corners, which creates these ugly, inaccurate sawtooth waveforms instead of smooth curves. It also creates this bizarre and misleading glitch that engineers call chattering. And ultimately, when you try to simulate today's complex systems, the simulation just can't keep up. It crashes.
And don't just take my word for it. This quote from a research paper really nails the problem with chattering. Basically, the time-synced method just can't pinpoint the exact moment a switch flicks on or off. It's always a little bit early or a little bit late. So it constantly over- and undershoots, creating this fake, high-frequency noise that can completely mislead the engineers.
So, if the clock is the problem, what's the solution? This is where the breakthrough comes in. It's a total paradigm shift. What if we just forgot about the clock? What if we stopped worrying about time and instead focused only on the moments that actually matter? And that brings us to event-based synchronization. Instead of syncing to the relentless ticking of a clock, the system syncs to events. The controller in the simulator only talk to each other and update when something important actually happens. In short, we've untied the simulation from the clock. It's a whole new way of looking at the problem.
Let me give you an analogy that makes this super clear. The old time-synced way is like live TV. You have to capture every single frame in perfect real time. If you're too slow, you just miss the action. This new event-synced way is like making a stop-motion animation. First, a key event happens, let's say a switch flips. The simulation then effectively hits pause. It takes all the time it needs, no rushing, to calculate the perfect result for that one instant. Finally, once the result is perfect, it captures that keyframe and the simulation jumps forward to that new state. The result is always accurate because it's no longer in a race against time.
Okay, so you're probably wondering what exactly counts as a keyframe or an event here. Well, it's any moment that something important changes. A power switch flipping on or off, a diode starting to conduct, or the controller itself taking a measurement of the system. These are the moments that define the system's behavior, and they're the only ones we need to capture perfectly.
And I have to tell you, this stop-motion approach, it's not just a minor improvement. It's a game changer. Freeing the simulation from the chains of real time unlocks this amazing cascade of powerful benefits.
First up, efficiency. I mean, just look at this number. Researchers built an interface based on this event-driven idea, and they achieved a staggering 394-fold, that's not a typo, a 394-fold reduction in the time the computers waste just trying to stay in sync. Simulations are now wildly more efficient.
And what about accuracy? I mean, being faster is great, but is it better? Well, take a look at this. If we use this new event-synced method as our gold standard, our baseline of 1, the old time-synced method is nearly 40 times more inaccurate. It's not even close. By taking the time to calculate each keyframe perfectly, we basically eliminate simulation error. But for me, this is the real kicker: the cost. Because this new method isn't being rushed, it doesn't need super expensive specialized hardware like FPGAs, which are these ultra-fast chips that can cost thousands and thousands of dollars. Nope, this can run on a standard PC. So the cost to do this high-fidelity simulation plummets from as much as $17,000 down to just a few hundred. This makes world-class simulation accessible to pretty much everyone.
And the benefits just keep stacking up. You can now link different kinds of simulators together accurately. You can build systems that are tolerant to faults, meaning they won't just crash if there's a communication glitch. It's efficient enough to do really detailed analysis of energy loss. And of course, it completely gets rid of that annoying chattering problem, finally giving us a perfect picture of how tricky components really behave.
So let's zoom back out. We've gone through the tech, but what does this all mean for the future of energy and transport? Now that we've broken through this technological barrier, we can start to dream a whole lot bigger.
I think this chart just says it all. If there's one thing to take away, it's this. We are no longer limited by the raw speed of our hardware. The scale of what we can simulate has gone from being strictly constrained by the clock to being, for all practical purposes, unlimited.
And remember that massive 2-megawatt system we talked about at the beginning? The one with almost 600 switches going crazy? Well, we can now reliably test its entire real physical controller with a level of accuracy and detail that was just completely out of reach before. This isn't theoretical. It's a huge practical leap forward for real-world engineering.
So the bottom line is pretty clear. This breakthrough makes designing our future grids, our electric ships, our high-speed trains, all of it, faster, cheaper, and most importantly, safer. It allows engineers to test their most ambitious ideas accurately at a massive scale before ever breaking guard.
Which leaves us with one final, and I think really exciting question. We're no longer constrained by the clock. We're only constrained by our own imagination. So now that we can accurately simulate what was once impossible, what are we going to dare to build next? Thanks for joining us on The Explainer.